even a thunderstorm, but generally there's not any warm air or cold air moving. The weather along these fronts is similar to warm fronts, less turbulent, sometimes even much, much longer lasting. You get a stationary front, it doesn't move. It can stick around for a couple of days, where a warm front typically is moving to the north. Now, we do see this in our fall and our spring seasons in central Florida, where cold fronts can advance all the way down the peninsula. They get stuck, and then you get a stationary front with some slightly denser air to the north, slightly less dense air to the south, and all the moisture of the Gulf and Atlantic just sort of providing showers. And that's when we get those gray days that may go on for 2 or 3 days. So there's no large-scale advancement of warmer or colder air. The stationary front is marked by alternating sections of red and blue, indicating, again, it's not moving in either direction. Sometimes a cold front, as I mentioned in Florida, or even in other parts of the globe, literally, a cold front can be marching along with cold air behind it and advancing to the south. And as that colder air warms, the further south it gets, the density differences become negligible, and that cold front will stop. And sometimes even stretch out and become elongated. And that's very typical when they transition, a cold front transitions into a warm front. And a cold front transitions into a stationary front. And sometimes warm fronts can transition into stationary fronts as well. Now, throughout the coursework, we have looked at cold fronts and warm fronts, and oftentimes when we've seen mid-latitude cyclones or extratropical cyclones, we've seen that purple front with both the pips and barbs moving in the same direction, but it's purple, and those fronts are known as occluded fronts. And occluded fronts are simply where faster moving cold front or a faster moving cold front catches up and overtakes a warm front. So it's where colder air catches up because of higher density and overtakes warmer air. And sometimes that warmer air is cool as well, but the bottom line is the colder air is colder. And again, it's a purple line with alternating pips and barbs. And there's generally 2 separate types of occluded fronts. And one is where very, very cold air lifts up slightly cooler air, because it's a very, very cold air advancing, and it lifts up slightly cooler air. And that's going to be in a typical mid-latitude cyclone traveling across the country with the cold air coming in from the north and catching up to the warm front. There's another situation where we have more humid air, so it may not be quite as cold, and that cooler air catches up to a colder air mass, and then it's lifted up and over the front. And that occluded front is known as a warm type. So a cold occlusion occurs when the air behind the occluded front is colder than the air ahead of it. The cold occlusion acts in a similar way to a cold front in that the cold air behind the front undercuts the cool air ahead of it. Whereas a warm occlusion occurs when the air behind the occluded front is warmer than the air ahead of it. The warm occlusion acts in a similar way to a warm front in that the cool air behind the front is lighter than the cold air ahead of it, and this causes the cool air to pass over top of the cold air. So we're not going to necessarily focus on the nuances of cold type or warm type. What we want to understand is the general concept of an occluded front as being where the cold air has caught up to somewhat warmer air, and an occlusion occurs. And literally, the occlusion is where that warmer air is lifted up, and that's what creates the rainfall along it. So this is what an occluded front looks like from both the warm occlusion or the cold occlusion. Now, these illustrations are set up a little backward. The beginning point is at the bottom, and then at the top is the end of it. So at the very, very bottom is what it looks like on a surface map. So I'm going to start with that warm occlusion, where an extratropical or a mid-latitude cyclone comes on shore off the Pacific, and that cool Pacific air it creates the cold front, moves into a region of warmer air, but eventually the cold front catches up to the warm front, and the cool air then has to move up and over the colder air that we see inland from the Pacific Ocean. So that's the very bottom left illustration. That's the way it looks in the surface, and that purple line, of course, is the occlusion. So just above it, is that cooler air advancing, and possibly with showers and thunderstorms, because it's a typical cold front moving into warmer air, creating an unstable environment and clouds of vertical extent. At the same time, that warm front is moving out ahead of it, but more slowly, and it's creating that stable environment in the stratiform clouds and showery precipitation. And eventually that cold front with the cool air behind it catches up to the warm front, and that cooler air literally slides up and over that colder air, and that is the warm occlusion. And you sort of have a mixture of both thunderstorms and showery precipitation with that. On the right is our cold occlusion. Now, at the very, very bottom, that's the way it looks on your surface weather map. And again, a very typical mid-latitude or extratropical cyclone with your low, your cold front extending to the south and west, and warm front extending to the north, to the south and east, that is. And eventually that cold front near the low catches up to the warm front. And where the cold front catches up to the warm front, that's where the occlusion begins. And in this case, very cold air is catching up to colder air. Ahead of the warm front, there is cold air. But behind the cold front, it's very cold. And so if you look at A just above the surface map, we can see the very cold air marching along into that warm sector. And with cold air over warm, you get an unstable environment and clouds of vertical extent and thunderstorms. And then once that cold front literally catches up to the warm front, that is the initial occlusion. And one thing you need to recognize is at the initial occlusion, that is when this mid-latitude cyclone is at its most powerful. That's the deepest point of the cyclone and where it is strongest. So we can see at B, where at the initial occlusion, we have a mixture of thunderstorms and showers. And then as that very cold air undercuts that colder air, so density differences, very cold, more dense, cold, less dense, and lifts it up, you tend to get more showery precipitation. And that is your occlusion. We have talked a lot about the mid-latitude cyclone, also known as the extratropical cyclone, or sometimes middle-latitude cyclone. And in the text, they do refer to it as a wave cyclone as well. We've talked a lot about that, the combination of the low, the cold front, the warm front, and eventually as that cold front catches up to the warm front, our occluded front, the counterclockwise spin around that feature, the thunderstorms along and ahead of the cold front, the showery precipitation and snowfall out ahead of the warm front. But let's begin to detail how that actually develops, the life cycle of that particular weather feature, and then we're going to talk in detail how the upper levels of the atmosphere impact, enhance, and then weaken that mid-level cyclone, that mid-latitude cyclone. All right, so the polar front theory is essentially something that the Norwegians came up with in the 1920s. And we were beginning to understand the three-cell model at the time, and that at somewhere around 60 degrees north latitude, that polar front existed, separating the colder air from the cooler air to the south. And along that polar front, we had those polar easterlies, and we had the westerlies from the subtropical high. So the high pressure, if you look at A, the stationary front, the H represents that polar high. The H to the south of the front represents your subtropical high, and of course you see your wind flows. And so essentially, that is kind of a static situation, creating that polar front at about 50 to 60 degrees north latitude. Now, upper level disturbances, and we'll detail those in a moment, create cold air advection and warm air advection. And remember, advection is the horizontal movement of air. So cold air advection is that cold air moving from south to north across well, not across, but pushing south into that stationary front. And the warm air advection is that warm air, more humid air pushing north. And so as those air masses begin to move, we no longer have a stationary front, but we have a cold front and a warm front. Now, as that low itself begins to move as well, because the low only forms once that cold air advection forms. And as the low begins to move along, typically to the east, we can see that cold air wraps around and the warm air lifts north. The green shading in both B and C representing precipitation along those boundaries. And then as we take it down from a stationary front to a frontal wave to an open wave, so that open wave in C is the mid-latitude cyclone, in which there is a cold front and a warm front that are not connected. There's no occluded front. And so very important to understand that between that cold front and the warm front is the warm sector of the mid-latitude cyclone. That's where you find the warm sector, the south to southwest winds, the warm humid air of the mid-latitude cyclone. Now, at D, you still have a warm sector, but you also have the initial occlusion. That is where the cold front first catches up to the warm front. And at this point is when the mid-latitude cyclone is at its most intense, because, and this is important, mid-latitude cyclones are provided their energy by temperature differences across horizontal differences. So where you have significant temperature differences, you're going to have a significantly deeper mid-latitude cyclone. And then where you have less temperature difference, you're going to have a weaker mid-latitude cyclone. So as that initial occlusion begins, that is where we find the mid-latitude cyclone at its most intense, in that mature stage. That's when it deepens the most, and you can see as we advance to E, where there's more isobars around that low, indicating a deeper low. And then eventually, as that moves off to the north and east, that low becomes cut off. It leaves a warm front, a stationary front behind, and you see the dissipation of that mid-latitude cyclone. So this is the very, very general life cycle of a mid-latitude cyclone. But again, a couple of things to remember. The energy is provided by the temperature differences. Colder and warmer air provide the energy for the mid-latitude cyclone. It does reach its mature state at the initial occlusion, and that begins the most intense portion of the mid-latitude cyclone. So we said that the mid-latitude cyclone begins when cold air advection begins. Remember in the previous slide, we had the stationary front with cold air to the north and warm air to the south. So what causes that cold air advection to develop at the surface? Well, what causes that is literally cold air advection in the upper levels of the atmosphere, or a trough of low pressure, a low pressure in the upper levels of the atmosphere representing colder air aloft, begins to move south. And in our left side of this illustration, we can see that developing trough of low pressure in the atmosphere. And you can see where the air parcels are moving into the trough, they are converging. They're getting closer together, just like the cars going around the Fairbanks curve in I-4. And as they get closer together, they're also going to slow down. And that is your convergence. They come together, they converge. And since that is the top of the atmosphere, the air can't go up, so it goes down. That creates sinking air and high pressure at the surface. And then in the exit region of that trough, that is where there's divergence aloft. And that divergence, air is being evacuated. It's being moved away. It can't be replaced from above, so it's replaced from below, creating air that is rising off the surface. And that rising air off the surface is what creates the counterclockwise turn of the low pressure at the surface and that cold air advection. So the upper levels of the atmosphere initiate the low at the surface. So convergence and divergent patterns aloft are extremely important to the development of mid-latitude cyclones. Diverging air deepens cyclones. So on the right side, it's diverging air, that air moving away where it says DIV, deepens that cyclone at the surface. And then on the left side where it says converging air, that builds an anticyclone, or an anticyclone is created. So convergence is where air piles up, net inflow to a region, and divergence is where air spreads out, net outflow from a region. So convergence and divergence can also occur when winds slow down or when winds speed up, or when those contour lines converge or diverge. And so the chart on the right is just a very, very similar situation, just a more simplified view with the upper level trough creating the cold air advection at the surface, because as the air sinks in the entrance region of the trough, the sinking air spreads out and turns right, creating that northwest flow. And as the air diverges in the upper levels of the atmosphere, the rising air creates counterclockwise flow and that north to northwest flow around the low. And that's what gets that cold air going. And so we go from a low at the surface to a low with a cold front and a warm front, our open wave, with the warm air being the warm sector, and that is your mid-latitude cyclone. So it takes a trough of low pressure, or at the very least, divergence in the upper levels of the atmosphere to induce the high. The divergence induces the low at the surface, and the convergence in the upper levels of the atmosphere inducing the high at the surface. So those waves in the upper levels of the atmosphere, both these illustrations at the bottom are showing the 500 millibar level, so that's above that level of the upper levels of the atmosphere. Those waves, whether they're troughs